Hey everyone, and welcome. Today, we're going to tear down one of the most important and influential storage systems ever designed, the Google File System, or GFS. This is the architecture that really set the stage for how we handle big data, and you'll see its DNA in pretty much all the cloud systems we rely on today.
So let's just start with the absolute core question that Google was facing back in the day. How in the world do you store, an internet's worth of data when you're building your system on thousands of cheap commodity computers that you know are going to break all the time? That single challenge is what sparked the genius behind GFS.
So here's our game plan for this explainer. First, we'll look at why Google even needed to invent this thing. Then we'll get into the actual architecture, meet the key players, and take a deep dive into the master node, the brains of the operation. After that, we'll untangle their model for data consistency, see exactly how data gets written, and wrap up with a really cool concept, how GFS embraces its own imperfections.
Okay, let's get into it. To really appreciate just how clever the GFS design is, you first have to understand the very specific, kind of weird set of problems they were trying to solve. They weren't just building another file system. They were building something for a completely different reality.
And these were their core assumptions. First, and this is a big one, failure isn't an exception. It's the normal, expected state of things. Stuff is always breaking. Second, they're not dealing with little Word docs. Files are enormous. We're talking hundreds of megabytes, often gigabytes. Third, most of the time they're just adding new data to the end of these files, what's called an append. And when they read the data, they read it from beginning to end, like streaming a movie. Because of all this, getting a huge amount of data moved over time, that's high bandwidth, was way more important than getting a super fast response for a single tiny request. That's low latency.
So to wrangle these giant files, GFS made a critical design choice. It chops every single file into these big, uniform 64 megabyte chunks. Just think of it like deciding that every package in the world has to be in the same standard size shipping container. It makes managing, finding, and copying just petabytes of data so much simpler because every piece of the puzzle is the same size.
Okay, so we've got the why. Now let's look at the how. What does the actual blueprint for this system look like? Well, it really just comes down to three main components working together.
And here they are at the three key players. You've got the GFS client, that's your application. You've got the GFS master, that's the traffic cop, the brains of the whole outfit. And then you have the GFS chunk servers. These are the workhorses that are actually storing all those 64 megabyte chunks of data.
All right, let's break down this diagram because it tells you almost everything you need to know. See those two types of communication? An application using the GFS client first pings the master. It asks a question like, hey, where can I find the fifth chunk of file ABC? The master doesn't have the data, but it knows everything about the data. It sends back a list of locations. Then, and this is the most important part, the client talks directly to one of the chunk servers to get the data. The master is out of the loop for the actual data transfer. This separation is absolutely crucial for the system's performance.
Let's trace that read request step by step. First, your app asks the master for a specific chunk of a file. The master looks it up in its memory and zips back the chunk's unique ID and a list of chunk servers that have a copy. The client then caches that info for a little while and pings the best chunk server, usually the one that's physically closest on the network. Finally, that chunk server just streams the 64 megs of data straight to the client. The master isn't involved in that heavy lifting at all.
Now, let's zoom in on that central coordinator, the master node. You can really think of it as the all-knowing, all-seeing librarian for the entire GFS cluster. It knows where every single book, or chunk, is.
The master's job is to manage all the metadata, and I mean all of it. It knows the entire directory tree, it knows the map of which files are made up of which chunks, and it keeps a constantly updated list of where every copy of every chunk lives. And to make things super fast, it keeps all of this information right in its RAM.
But the master isn't just a passive address book. It's constantly working behind the scenes, kind of like a tireless sysadmin. It's always scanning to see if a chunk server has dropped offline, which would mean some chunks don't have enough copies. If it finds one, it immediately orders a new copy to be made. It also cleans up the data from deleted files and shuffles chunks around to make sure the load is balanced evenly across all the servers.
All right, let's shift gears to something that can get a little mind-bending in distributed systems: data consistency. When you have multiple copies of your data scattered everywhere, how do you make sure that what you're reading is the right version? GFS has some very specific promises it makes.
So the first promise is a state called consistent. This is simple but really powerful. It just means that if GFS tells you a piece of a file is consistent, every single client that reads it will see the exact same data no matter which copy they happen to pull from.
But there's a higher bar, which GFS calls defined. For a region to be defined, it has to be consistent, and clients have to see the results of a change, a mutation, all at once. There are no partial updates. You either see the whole change or you see none of it.
Now this table right here really pulls it all together. A normal, successful write leaves the data in a defined state. Simple enough. But here's the wild part. Look at a concurrent success. That's when multiple clients write to the same spot at the same time. The result is consistent but undefined. What on earth does that mean? It means the data isn't corrupted. It will contain the complete data from one of the clients. But GFS makes no promises about which one. It's a race, and somebody wins, but the system doesn't tell you who.
Okay, so knowing those consistency rules, let's look at the actual mechanics. How does GFS perform a write operation to make all this happen?
It's a really clever three-phase dance. First, the client asks the master, hey, who's in charge of this chunk right now? The master picks one of the replicas to be the primary and gives it a short-term lease. Second, the client pushes the data it wants to write to all the replicas, the primary and the secondaries. They just hold onto it in a buffer. Finally, the client tells the primary, okay, do it. The primary then picks a serial number for the write and tells all the other replicas to apply that change in that exact order. That's how they all stay in sync.
Now in append, just adding data to the end of a file is almost identical, but with one little twist in phase 3. Instead of telling the primary where to write, the client just says, append this. The primary then figures out where the current end of the file is, writes the data there, and then tells the other replicas the exact spot it shows. The important thing here is if anything goes wrong, the client is programmed to just try the whole thing again. This gives you what's called at least once delivery.
And that at least once idea brings us to a core piece of the GFS philosophy. The system doesn't try to be perfect. It doesn't solve every single problem. Instead, it forms a partnership with the applications running on top of it, and they share the responsibility. And this right here is just brilliant. Think about it. Because a client might retry and append, you could accidentally write the same piece of data twice. GFS doesn't try to prevent this. Instead, it says, hey, application, that's your problem. So applications built for GFS are expected to put unique IDs in their records. Then, when they read the data back, it's their job to check for those IDs and throw away any duplicates they find. It's a shared responsibility model.
Which brings us to our final thought. The GFS paper came out way back in 2003, but its core principles, designing for failure, using replication for safety, separating the control messages from the data flow, and pushing some complexity up to the application, these ideas were revolutionary. So the next time you use something like Amazon S3 or Azure Blob Storage or HDFS, take a second and think, which of these foundational GFS ideas do you see still running the show today?